Hello, everybody. Welcome to my basement. We're going to have our first asynchronous lesson, which should be pretty short and sweet. We're finishing up optimization. So the thing that I want to do is just go through one example. We've done a couple in class. Hopefully you've been working on them and making some progress on this idea, but I would like to do one more. It's actually the last problem from your homework assignment. I believe the problem is number 77. It's about a bird who is trying to make its way to a nest as quickly as possible. Pause me, go read the question, digest it a little bit, and then come back and we'll take a look at it together. All right. All right. Now, seriously, if you haven't read this problem, stop this video, go read the problem. I'm not kidding. This is going to be a waste of your time if you haven't thought about this problem already. One last chance. Pause the video, go read the problem. Okay, now that you've read this problem, you've thought really hard about this, you've thought about parts A, B, and C, what does all this stuff mean? Here's the idea. Got this bird that's sitting on an island out in the water, 5 miles straight out from the shoreline. And then from the point that's closest on the shoreline, it's 13 miles to get to the nest. And so this bird wants to fly to the nest. Now, according to the people who wrote this problem, it's more difficult to fly over water than it is to fly over land for whatever reason they come up with. So I want to think of a couple different scenarios. This has to do with what you do in the first part of the problem. Suppose, hypothetically speaking, that flying over water is no problem. Water, land, doesn't matter. Then the answer here, what path should the bird take to get to his destination? I want a little dotted line thing here. I'm going to make this one a dotted line. If that's the case, well, then this bird's going to take off. He's going to fly straight to the nest, and this is just a Pythagorean theorem problem. 5 squared plus 13 squared, take the square root, whatever that is. That's our answer. Easy peasy. If flying over water is really difficult, if it takes like 1,000 times more energy to fly over water than land, for whatever reason, well, then this bird is going to spend as little time flying over water as possible. Its path is going to be almost straight to land. Maybe I'll give him just a little tiny bit of angle because that's not much more of a difference. And at least we can see something that's going on. And then from there, it takes off and it heads straight to the nest. It's flying a greater distance, but it's minimizing the amount of time or energy that it's taking flying over the water. Another scenario that isn't covered by the book, what if it's even easier to fly over water than flying over land? Well, this is kind of the same as the first case. I'm just going to make a straight line. This is the easiest path. I'm flying over water, which is totally easy, and it's also the straight line. So that's going to be the same answer. Now, the more interesting case is the one that they're asking us about. What if flying over water is, for some reason, mysteriously 1.4 times more difficult than flying over land? Well, that means we're going to have something that's kind of in between those first possibilities. I'm not going to fly straight this way because then I'm spending a lot of energy flying over water, which is apparently difficult. But I'm not going to go straight to the shoreline because then I'm flying quite a bit longer distance. So my answer is going to be somewhere in between. I'm going to find some point somewhere on that shore, head toward that, and then I'm flying just a little bit longer than the straight line, but I'm also not spending too much time flying over the water. Where is the sweet spot? That's what this question is asking. So I'm going to stay on this slide because I've got the diagram, but I'm going to start labeling some things on the diagram. Now, first of all, this distance is significant. The distance that the bird flies over water, the distance that it flies over land. Those are both pretty significant quantities. And I'm trying to decide where I want to put the X. I think where I'd like to put the X, and I believe the book even suggests this. I forget if the book suggests something, but I'm going to put an X here to be like, what is the distance away from that straight line that the bird should target to minimize that total distance. Now, I need to get these distances in terms of x. This one's going to be easy. If the straight line total distance from one place to the other is 13, and x is the distance along this part of the triangle, well, then this distance is just 13 minus x. And that's not too bad. So he's going to fly 13 minus x miles at, well, the easier energy expenditure rate. And then this distance, the distance from the bird to the place where it hits the shoreline, well, that's a Pythagorean theorem problem. 5 squared plus x squared equals that distance squared. So this distance ends up being the square root of 5 squared plus x squared. Again, just coming from the Pythagorean theorem. So as I look at my equations, what am I trying to figure out? I'm trying to minimize the amount of energy that this bird is spending to make this trip. So I'm going to say that I've got this energy function. I've got the distance that it flies over water. I've got the distance that it flies over land. And flying over water is 1.4 times more difficult. So my energy function is going to be, well, 1.4 times that distance that it's traveling over water. I'm going to call that 5 squared 25. By the way, a Friedman number, 25 is 5 to the 2 power. I can take the digits of the number and rearrange to make the same value. That's a Friedman number. We saw one of those with the number of the day earlier this week. Or no, late last week? Whenever. Anyway, plus the amount of energy that it's going to spend. I'm going to call it 1 for now. Flying over that distance of land, 13 minus x. Now, the way that I've set this one up, I only have one variable. I suppose I could have called one of these distances W and one of them L to stand for water and land, and then I would have gone through the manipulation to convert and get it in terms of one variable. But I've already got that. I've already got my energy as a function of x, which means I can go ahead and differentiate. Solving this is going to be a little bit of a pain, especially since I'm writing with a mouse. But let's see, I've got mine written on paper. So I'm going to save myself a little bit of time and say that my derivative function, my e prime, let's see, I'm going to have 1/2 of 1.4, so 0.7 times that stuff, 25 plus x squared, to the negative 1/2 power, times the derivative of the stuff inside. Derivative of 25 plus x squared is 2x. That's times 2x. And then plus the derivative of 13 minus x. Well, that's just negative 1. Here we go again. I've got something minus something. I'm going to set this equal to 1. I'm going to simplify some of that left part of it. I've got a 2x times a 0.7. I've got something raised to a negative 1/2 power. So let's see, 0.7 times 2, we're back to 1.4. But I've also got an x. That stuff to the negative 1/2, I'm going to call that the square root of 25 plus x squared in the denominator. Minus 1 is equal to 0. Which, a couple ways of thinking of this algebraically, this fraction needs to be equal to 1 because then 1 minus 1 equals 0, or you could add 1 to both sides and then multiply both sides by the denominator. But either way, I'm going to end up with 1.4x equals the square root of 25 plus x squared. When I was working on this problem earlier, I thought that this probably meant that I'd have to resort to just graphing on my calculator and finding what the solution was. But it actually turned out that I could do this one algebraically. So I'll show you how I did it. This one actually works out not all that bad. I'm going to square both sides of this equation. 1.4 squared, well, I know 14 squared is 196. So 1.4 squared is 1.96. X squared. And it was at this moment that I squared the radical that I thought, oh, I guess I'm going to be able to do this. I won't even need quadratic formula because I don't even have an x term. I'm just going to subtract x squared from both sides and get 0.96 x squared. Whoops, 0.96 x squared equals 25. I'm going to divide both sides by 0.96 and then take the square root, and I end up getting x equals the square root of, sorry about that, 25 over 0.96. The square root of 25, of course, is just 5, but then the square root of 0.96 isn't such a nice number. So eventually I did have to bite the bullet and plug this into my calculator and find that x is about 5.103. It didn't come out to a number that was very nice. But there we go. That tells me that the bird should find a point that's about 5.1 miles. So in reality, we're looking at almost a 45, 90 triangle, an isosceles right triangle. So head out at a 45-degree angle, and we will minimize the amount of energy that will be spent flying from one place to the other. Whew, there we go. There's one last optimization question. Make your way through the other optimization problems. Let's see, we will be synchronous on Monday, so we can touch base and see how everybody's doing, but I would like to move on to something called antiderivatives on Monday. Spend some time on optimization this weekend, hopefully start to feel more comfortable with it, maybe even try some of those other problems, see how that goes. But good luck with this, and have a restful, safe weekend, and I will see you all on Monday. Bye-bye.